Okay, so let's begin again. I had a small mistake in the example I showed. I forgot a division by 15. So that's why the numbers looked kind of strange. The approximate error is the difference between the one interval approximation minus the 2 interval approximation, which will give you, well, first these numbers. So this is just the approximation in the 1 integral minus the approximation in the 2 interval gives us this number, and if you divide that number by 15, you get what I wrote. So I've basically just forgotten this here. Then it should be correct. So just divide it by 15 in the notes. And then you can see that, yes, it is slightly higher than the actual error. So this gives us the actual error, this gives us an approximated error, and they are of the same order. So that's my mistake. But then we'll continue with the implementation of adaptive quadrature. So this will be a repeat of the algorithm I showed, well, 50 minutes ago. So we are trying to estimate, let's actually try to estimate the same integral, so pi divided by 2. This is our function f of x as the sine from 0 to pi half. So this is the same as in the example. I have given it a tolerance of 10 to the power of minus 12, because that's, well, etiquette, and then a maximum depth of the recursion of 20. And I'll get to what this actually means. Again, you start with calculating the h. Well, that's b minus a divided by 2, or 0.5 times b minus a. You do the function evaluations. So this is so that you only need to do the function evaluation once. So you assign the variable fa, the value of the function evaluated at the point a and c and b. And then you start the approximation or the routine. So what you give it, you have to give it the function, because there will be more function evaluations inside this routine. So this is the f here, and this is the function evaluated at different points, fa, the midpoint, and then the right endpoint. This is your interval from a to b, and the step length. I mean, if you want to be minimalistic, you can make do with just some of this, because, for instance, you know that a plus 2h would give you b, but to make it simple, we'll just give it everything as an input. Then you have the tolerance, which I defined earlier, and then this is the first approximation, so using the full interval. This is the level we are starting at, that's 0, and then this is the maximum level, this big N, or the deepest level we want to go. And then I've compared it with the built-in integral routine of MATLAB, which you see only requires the function and the interval endpoints, A and B. And of course, it takes many more inputs if you want, but we're not looking for that right here. So then, looking at the actual function adaptive, this is starting from step, let me find my notes again. Yes, so this is starting at step 2, or actually 3, as I said it. So you are increasing the level you're at. you have to define a midpoint of the current interval you're at and halve the step size for the sub-intervals. And again, you would then need two more function relations, fd and fe. So again, our interval now looks like, maybe I can, it looks like you have an A, C, no, A, D, C, E, and B. So that's your interval points down here. Then you have the function evaluations at those points as well. Next, you have to actually do the evaluation, and here I've just basically said the Simpsons rule. Instead of calling a function called Simpsons, you can just basically plug it in there. And then you calculate the error as in the steps. Then next, to check if you're high enough in your recursion. So if not, well, then you, in order to avoid an infinite recursion, then you have to stop it sometime. And that's why you throw this error message. If the error is less than 15 times your tolerance, then you can start climbing upwards. Actually, this is better if you have less than, then it's a bit more accurate. And again, I've tried to explain that this corrective term here comes from Richardson explanation. So this means that if you remember from, I guess that was Tuesday as well, the degree of position of the Simpson method is 3, which means that it can integrate functions up to an order of polynomials of order 3 without introducing errors. Introducing this or using this small correction, you actually increase it by 2 degrees, so degree 5. So there's no reason why to not include it. And then you have the interesting bits. This is the else. So if you are not satisfied, so if you haven't gotten your exact or the accuracy you want, then you need to run this function again. And this is why this is a recursive relation. So here you see I have to use the function again. So here I call it first for the left side. And then you see again you have to input the function, but now these function evaluations and the interval is different. So now we see the interval is from A to C, and also you can give it the FA, FD, and FC. So that is basically just these points. So you are kind of treating it as the same problem, only with a smaller, only with a different interval. And again, you should also give it a tolerance, a lower tolerance, well, half the tolerance, because now you have divided into 2, so then you want the same, well, you don't want the same error, you want the error to be split equally between the 2 intervals, which is why you give it half of the tolerance for each. So this is actually stricter then. So when you go down a level, you have a stricter set for the tolerance in order to actually keep the tolerance when you then sum up again. So I can try to illustrate this a bit. So say that you have your starting interval. So what does this recursion mean? Well, you start at the level n equals 0. Then you have your whole interval like so. And then you do just 1. So this is your function. And then when you start calling this adaptive, you split this interval into 2, like so. And then if this gives you a good enough error, then this is fine. Then you can just stop. But more probably, it won't be good enough. So then you have to split this again. So then we get a sub-interval looking like, see, like this down here. And then you can go even deeper. So then this is going to be level 2, level 3 down here. That's it. Yeah. And the way this is implemented is that it could be that you have good enough, I guess this is going to split again. It could be that this gives you a good enough estimation over here, but at the left-hand side, you have to go a few levels deeper. So this is why it's called a recursive relation. So you are kind of splitting your intervals into smaller and smaller chunks with a tighter and tighter arrow control. And then this is why you have this big N, which is the how low can you actually go? Because there is a end to this. Now if you actually try to run this, you see that it gives us, it gives us 0.99999 recurring. And it's actually the same approximation as MATLAB. So we've done a good job. The target error we were looking for, so this is the tolerance I've given it. This is 10 times, 10 to the power of minus 12. And the pessimistic error, this is basically, I can show it down here. So what I've done is just taken the maximum error. So you are given an error estimate for this interval and this interval. And since you divide it in two, if you just take the maximum of those two, then you give a pessimistic error estimate of this level. Huh? Does that make sense? And then again, the maximum number of levels is 8 in this case. Say again? Oh, it's just pessimistic. Most probably your error will be lower than this, but you are assuming the worst. So you see here, I could be optimistic. I could take the minimum of these two errors instead. Then you see this is a much lower number. So this is an optimistic error estimate. But it is better to be pessimistic, so assume the worst when doing this. So the maximum here. Yeah. So here you see we have done 8 levels, so 8 splittings of this algorithm. So what happens if we are just too picky? So we want to be have a much lower tolerance. I think this is going to crash now. Yes. So you see, the problem with this recursive relations is that it throws the error many times because you will be at the lowest level many times, as you can see here. And it doesn't. So deepest level exceeded. An error in all of the instances, all of the lowest levels will just throw the same error. Again, let's see. 19 doesn't work. If I change this to pi, we should get that. Yeah. Or routine in this case isn't as good as the MATLAB approximation, but that's because the tolerance is also lower. I think the default tolerance of the MATLAB implementation is -12. So we can try. And then it's good enough. There's some discrepancies at a very, very small number. But yeah, it doesn't really matter. And again, the pessimistic error is almost a power less than the target error. So this works. And I will upload this to the Slack channel and the GitHub. So you can try to look at this yourselves if you're interested in recursive relations. Oh, come on. So next up is Gaussian Quadrature, which I've been asked about earlier as well. And Gaussian Quadrature is basically how to pick your points, your, well, again, interpolation, in such a manner that you get a better approximation of your integral. So up until now we've used Simpson. Now we'll go back and look at the trapezoidal rule again. So first some illustrations. It's wet. Gaussian Quadrature. Yep. So I'll just briefly draw two of this. So say that you have your function like so. Let's see. And again. Oh. So what we've done earlier is we've just picked the endpoints. We picked these 2 points. Like so. So then you see we get a gross underestimation of the integral here. And in this case, we get a gross overestimation of what the error is really. Now the thing with Gaussian Quadrature is that you want to pick some different numbers, not the endpoints. So it, for instance, could be this one and this one. And you will get a line going like so. So you see it's the same shape, it's the same length of the interval. Only that instead of always undershooting, you are in the beginning here overshooting and then undershooting here. So do we have more colors? Where's yellow? So you see you have a small piece here which you want to kind of substitute for this. Whereas here it's like everything here is just wrong. Also here, everything here is wrong. And equivalently, for this case, you would want to have points closer inside. such that you are here underestimating, you're overestimating in this region, and then you're underestimating again. And hopefully these two will cancel. It will nevertheless give you a better approximation of your integral if you pick these points. So the idea behind this is that you have nodes, let's just call them x1, x2, all the way to xn, and then you have some weights or coefficients. Let's call them c1, c2, all the way to cn. And then you want to pick both the x's and the c's, the weights. Let's see, I'll remove the screen, such that your integral from a to b of x dx is approximately the same. Ci from 1 to n, ci of xi. Like so. And just by looking at this, if you pick these points as, well, 1, 4, 1, and this as, well, the endpoints and the midpoint, then you get the Simpson rule. But that's not the point here. We want to pick this in a different way. I mean, this is just a general form. The assumption we're going to make behind our chosen points is that we want this to fit to a given polynomial. So we are assuming that we have a polynomial of degree 2, so n equals 2. No, n equals, so this is the amount of points. So this is this n, meaning that we have x1, x2, and c1, c2. And the interval -1 to 1. Then we want to determine these numbers so determine x1, x2, c1, and c2 such that the integral of a function from -1 to 1 dx is as close as possible to c1 times f of x1 plus c2 times function evaluated at the point x2. I want this to give an exact result. Whenever this function f of x is a polynomial of degree 2 times 2, well, n squared minus 1, which in this case is 2 squared minus 1 is 3. So this is just the basic case where we have n equals 2. You can also have n equals 50, but it's going to be more difficult to solve for. So a general polynomial of order 3, well, that's, I'm going to have to use f instead of p. A0 plus a1x power of 1 plus a2 x power of 2 plus a3 x to the power of 3. Well, what's the integral of this? Just quickly, from -1, well, not yet. We should first do the indefinite integral. 0 plus a1 plus a2, no, 1x plus a2x squared plus a3 x power of 3 dx. Well, 0 dx plus a1 x dx plus a2 squared dx plus 3 x power 3 dx. Yep. So requiring that the approximation is exact for this is requiring that you have actually the exact results when f is equal to 1, x squared, and x to the power of 3. So this is because if you want to look at it abstractly, you can begin to look at polynomial spaces, and the canonical basis of P3, the polynomial space of order 3, is 1 x squared and x to the power of 3, or x cubed. So if your approximation is correct for all of the basis elements, then it will be correct for all of the elements in this space. Did that make sense? So we only require that it is correct for the basis elements, and every other element inside the space is a linear sum of the basis elements. So if it's correct for all of the basis elements and you just sum the basis elements, then it will end up with the correct. Yeah, got carried away. Basically what we're after is we are first going to fit this for f1 of x equals 1, f2 of x equals x, f3 of x equals x squared, and, well, let me rename this 0, 1, 2, and f3 of x equals squared. So it has to be correct for all of these functions. Looking at this, so first we will do it for this. And well, every number we evaluate for this would just be C1 times 1 plus C2 times 1, because it's always 1. This should be equal to the integral from -1 to 1, well, 1 dx, which is 2. For the next one, we will have C1 times some kind of x1 plus C2 times some point x2 -1 to 1 x dx 0. So this is the integral of this function f1. Next we have C1 x1 squared plus C2 x2 squared should be equal to the integral from -1 to 1 of this f2 function, which is h2 squared. Dx should be 2/3. And then the latest one, C1 x1 power 3 plus C2 x2 power 3 x power 3 dx equals 0. So now we have 4 unknowns, which is C1, C2, x1, and x2, and we have 4 equations with this. So we can actually solve this. So do you remember what the degree of precision was for the trapezoidal rule? It was 1. Yeah. So the regular trapezoidal rule that had a degree of precision of 1. So it was only correct for linear functions. But how have we used the modification of it? So by picking these points in a good way, we see that we actually increase the degree of precision by 2. So this is correct for third-order polynomials, not only first-order polynomials. Just by picking the points in a better way. So continuing from over there, we have 4 unknowns with four equations, and writing this up, get a better stroke. We see that the weights C1, well, this is 1, and C2 is also 1. That's boring. X1 is -3, and x2 is plus square root of 3/3. Like so. So then we have, in this case, Gaussian Quadrature -1 to 1 x dx approximately equal to 1 times the function evaluated at the point -3 plus 1 times over 3. So we are slightly shifting where we are evaluating function. You certainly get a better degree of precision. DOP equals 3. And then it shouldn't be a big surprise that you can generalize this for any n. So here we had n equals 2. How does it look generalized? Oh, it's from solving these equations.
We don't know x1 and x2.
No, you don't. Yeah, 4 equations, 4 unknowns.
Okay.
So, let's see. Basically, you know that C1 and C2, C1 plus C2 are supposed to be equal to 2. And, well, they are, if both of them are 1. Next one, you have c1 times x1 plus c2 x2, oops, should be 0. Oh, that's what this says. Then you have c1 x1 squared plus c2 x2 squared should be 2/3. The only thing is these aren't linear equations, so you kind of have to solve them in a more complicated manner. X1 power 3 plus c2 x2 power 3. Like so. These are the equations you want to look. So 4 equations, 4 unknowns. It's basically the same that's here, only that you don't have this noise in the middle. I mean, just ignore this and you have the same equations. Yep. Again, remove this. Theorem. So we will assume that we have points x1, x2, all the way to xn, or the roots of the nth Legendre polynomial. Pn of x, like so. So now we're backtracking again. Now we're back to polynomials. Then the numbers. Ci are defined by Ci, and again you see we do an integral from -1 to 1, j equals 1, j not equals I to n minus xj, xi minus xj dx. Do you remember what this was? This is just the product, sum product of all of them. And then you do an integral. You only need to do this like once in order to get the constant. And again, you see that we have a problem. This only works for integrals from -1 to 1. But that's not really an issue, as we get to. If p of x is any poly of tag less than 2n, so up to 2n minus 1, oh, I did something wrong in the earlier. Do you remember when I wrote n squared minus 1? That's supposed to be 2 times n, not n squared. My apologies. Anyway. P of x dx I from 1 and ci p of xi, like so. Then we only have one issue left, and that is what to do for arbitrary intervals. So from AB. Well, then we need a transformation. So we introduce a t, which is 2x minus a minus b minus a, or equivalently that x equals a half b minus at plus a plus b, like so. Then we have that our integral from a to b, f of x dx is the same, minus 1 to 1, f of b minus a, b minus a times t plus b plus a divided by 2. So this is basically just this x that stands up here. B minus a divided by 2 dt, which you get from this. Meaning that a to b f dx can be approximated with b minus a over 2 I equals 1 and these same ci's, f of b minus a over 2 xi plus a plus b over 2, like so. And if you want to find lists of these points, these ci's and xi's, they're called Gauss-Legendre points. So I can write some of them. So when n is 2, you would have, this is the xi, it looks different than what I wrote earlier, but it's the same. So Remember this? And then you have the CI. That's 1 and 1. When you have for 3 points, you have 0 plus minus 3/5. But then you have weights as well. So you would have 8, 9, 5, 9, and 5, 9, like so. We could do one more, I guess. And then we start to see that these CIs and XIs are starting to get complicated. So again, we have now n is 4, then xi will be plus minus 3/7 minus 2/7 square root of 6/5 plus minus 3/7 plus 2/7 square root of 6/5. 18 plus square root of 30/36, and 18 minus square root of 30/36. And then for n equals 5, the analytical expression becomes more convoluted, but this gives you can just punch it in a calculator, look at them on a table, and you're going to get a good point of this. So yeah. CI. Like so. And sorry for going over time, I see. Any questions?